Good morning. All right, we're going to talk about exponential growth and decay, and this is section 6.5 from Stewart's Calculus. We're looking at the 7th edition, even though there are newer editions. Okay, now, um, there are certain things in the natural world that, at least for a little while, get modeled by this formula. It's that the rate of growth depends upon what's already there, or the rate of decay depends upon how much is there already. Okay, so what does that mean? When I say rate, and you're in a calculus class, the first thing that should pop to your mind is what? A derivative, right? The rate of change, which is the derivative, depends upon what we have already. Okay, so I can express that mathematically like this. The rate of change, so I'm going to say dy dt, t being time, right? The rate of change depends upon what we have. So it's some sort of constant times the initial function. All right, and this is the situation that we're looking at. And if k is greater than 0, so k is some sort of constant. If k is greater than 0, this means this thing is growing up. Okay, we call this growth. We call it natural growth. If k is negative, we call it decay, natural decay. And we'll look at examples of both of these situations, okay? But first of all, we got to figure out, can we actually solve this thing? All right, well, what kind of function has its, when you take the derivative of it, you get that thing? You're right, the, the exponential function. Okay, so we'll say a theorem here. It turns out it's not only a solution, it's the only solution. So the only solution to this, what we call a differential equation, this is a pretty simple differential equation, dy dt equals ky, are the exponential functions. Okay, and what you end up with as a solution is that the function y of t, the one that when you take the derivative you get the thing times a constant, is y of 0, so it's kind of like a starting point, like your initial population, e to the kt power, and that's your solution. Okay, so a few things to point out here. We call this a differential equation. We have a class on differential equations, which we talk about this and much more in depth. And I'm not too concerned about all the details on that right now. But your solution is a function. In this case, it's the function y. We are looking for y that satisfies this property, that when you take its derivative, you get a constant times that function. Okay? And again, what kind of functions do that for this type of differential equation? It's simply the exponentials. You take the derivative of e, what do you get? You get e again. And it may depend upon your what your value of k is and what your initial population was. Um, but this is the solution, okay? And we'll look at some examples of that. All right, now the two big things we already talked about, it was decay and growth. And so I'll give you some examples where we see this. So let's first look at population growth. And we can try to model how quickly a city's growing or a country is growing or bacteria in a petri dish, that kind of stuff, through this same technique. All right. So for population, we usually set it up to look like this. That you have a population function, and so your change in population depends upon how much population you have already, right? So the larger the city is, the quicker it's growing, that kind of thing. And so if you notice then, we could solve for k by just dividing both sides by the function p. And so we get k to be the constant k is 1 over p times the derivative. And we call this the relative growth rate. The whole thing here, this expression. The relative growth rate. Okay. And let me just use an example, and then I think maybe some of this stuff will make a little bit more sense to us on what we're talking about. Sometimes when we write it in general terms, it can be a little confusing. All right, so here's my example. All right, so we're going to look at world population. So in 1950, the world had 2,560 million. All right, that's a funny way of saying 2.56 billion, but we're going to write it that way. All right, and just so that our constants are kind of where we want them. And again, in 1960, so 10 years later, the world had 3,040 million people. Okay, so in other words, 3.04 billion people. All right, now what we want to do is we want to estimate what the world's population was in 1993, and then let's use this and see if this model is still holding for the year 2020. Okay, so we're actually going to be current. All right, so estimate population in 1993 is what we said, and in 2020. Okay, and let's see if we can figure this out. Now, this is a population growth model, so we know we're satisfying this differential equation, dp over dt equals kp. All right, we're going to let, if t is 0, so let's let t be time in years after 1950. Okay, so t equals 0 is 1950. All right, and we also are going to let p of t measure population in millions. That's why we had that 3,040 million. I mean, you don't usually say it that way, right? Okay, so what we know then, we have a couple of points. We know that p of 0 that's the population in 1950, would be 2,560. And we know that p of 10 is at 3,040. Okay, so these are my points. So all this is kind of part of my solution, and I'm not writing in complete sentences here, but we're just trying to figuring out some stuff. So I'm just going to write figuring it out right here, okay? All right, now we're assuming that the change in population does in fact follow this population growth model that we use. And so from my theorem, we said that that situation is going to have a solution y of t equals y0 e to the kt. So here I know that my solution, and we're not even bothering trying to figure out how that works because that's not the goal of this class, okay? We're going to say p of t equals p of 0 e to the kt power. So we know what p of 0 is, right? That's my initial population. That's 2,560 e to the kt power. All right, now we almost have my population model then. We just need to figure out the value of k. How can I do that? Well, that's why I have 2 points. Okay, so let me make a note here. It says the second point helps determine the value of k. Okay, so the second point that we have helps us figure out what the value of k needs to be in order to get this model correct. Okay, so we know then that if I plug in 10, I know what this is going to look like. It's going to be 2,560 e to the k times 10 power. And I also know what that's got to equal, right? The 3,040. We got that from right here. And again, I'm just plugging in values into this model right there. Okay. So now what that allows me to do though is figure out the value of k because I know everything in the situation other than k. So I get that e to the 10k power equals 3040 divided by 2560. So how do I do this? I take the ln of both sides. So 10k equals ln of 3040 over 2560, or k equals 1/10 ln of that number. And if you put that in a calculator, you should get, and I'm just copying the book's notes here, 0.017185. That is my value of k. So that tells me then that my actual model, the actual function, p of t, is 2,560 e to the 0.0170, let me try that again, 0.017185 t power. And that measures population in millions years after 1950. I hope that makes sense. Okay, now we didn't actually answer the question though, right? That's just the function that we needed. The question asked for, let me go back and look, population in 1993, the population in 2020. Okay, so then for 1993, in 1993, we are looking for what value p of, well, 1993 is how many years after 1950? 43. So I'm plugging in 43 there. So I get 2,560 e to the 0.01 blah 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 times the 40 times 43. Try and change my colors back. There we go. And this is just a matter of plugging in the calculator. We get approximately 5,360 million. Okay, so 5.36 billion. And actually, if you look up online how many people we were on Earth in 1993, that's actually pretty close. That's not too far off. All right, so according to this model, what about in 2020? So in 2020, we're looking for P of what? So 2020 would be 70 years after 1950. So I'm looking up, plugging in 70 in for t to the same model, e to the 0.017, blah, 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 the 70th power. If you plug that in, you should get approximately 8,524 million. Okay. And I looked it up last night. We actually have around 7.7 billion people now. So our model is kind of an overshoot of what's actually going on now. Okay, which is fine. These models, the exponential models, won't last forever. I mean, you wouldn't base the Earth's population in the year 3,500 based upon how many people are on Earth in 1950, right? That doesn't make any sense. You adjust the models as time go on, but for the first 43 years at least, this model was pretty good. Okay, now, so that's an example of population growth. I hope that makes sense. Now, a funny thing is that these models don't just apply to like a population of a city or the world. it can also apply to some interesting things like how quickly information spreads, um, how many articles in journals get published each year. These type of things grow according to these models. I read an interesting article one time where they were testing land speed records, and so they were going through the years from different technology. Like once the horse and buggy came along, land speed record was this, and then the car came out, and the land speed record went up, and so on. And they tested their model, and they said, okay, if this happens, then in so many years we should be able to leave the Earth's atmosphere. And exactly to their model, Sputnik, the Russians launched the satellite Sputnik and it made it into the atmosphere. And then their model said, okay, such and such years from now, if this model holds, we should be able to land on the moon. And then in 1969, exactly according to their model, we landed on the moon. So their model was actually measuring land speed records very accurately, even into the future. We call that extrapolation. And if that model holds, then within our lifetime, we should be able to reach speeds of interstellar travel, actually humans leaving the solar system within our lifetime. I don't know if that's going to happen. Let's hope it does, though. That'd be kind of neat. I know NASA's got some ideas on how to do some things like that, or at least some of the physics behind how something like that would be possible. All right, so anyway, exponential growth has some interesting applications. Okay, now let's look at the other side, decay. And typically when we're talking about decay, we're talking about radioactive decay of a chemical compound. So radioactive decay. And the model is the same. Okay, the only thing is this time K is negative. So we end up with MT equals M naught e to the KT power. And here M is like initial mass. Okay, so here we're measuring remaining mass. All right, so what happens is you have a substance, and due to the chemistry behind it, the substance starts decaying in the atmosphere, and sometimes it takes a long time to do that. And a particular term that's interesting to us is the half-life. So if you say the half-life of an object, what you're talking about is the amount of time it takes for, like, let's say you start with a kilogram of this substance, how long will it take before now you only have half of a kilogram? Okay, so this is the amount of time required to half a given quantity. And this is the idea behind carbon dating, is that we know the half-life of carbon, and so from that we can find a fossil or something and see how much carbon is remaining from what it should have had. And so we just kind of work backwards and figure out how long it would have taken for that amount of carbon to decay to what we have currently. And there's some things that could affect this. I mean, one, we're not exactly sure that the model would hold that long, um, though we feel pretty good about that. But there are other things like if this particular bone had been exposed to some sort of trauma, like the where is it in Italy, in Pompeii, the ruins of Pompeii date way older than they actually are because of the volcanic um, material, the lava and whatever, kind of decaying it more rapidly than normal. So there are some things that affect it, but this is one of the techniques that we use. Okay, so let me give you an example. Let me get some coffee first. Okay, so we're saying here we have some radium-226, and we know from experimentation that the half-life of radium is 1,590 years. Now, how do they calculate that? Again, it goes back to some differential equations. Um, and it's actually a very similar process to what we just did with population growth. All right, now what we're saying here is that we have a sample that has a mass of 100 milligrams. Find the formula for the mass after t years. So we want to find, kind of like we found our population growth model, we want to find our radioactive decay model. Okay, so let me show you how that works. All right, now we just said that, look, we use this MT. We know MT equals M naught e to the KT, right? And we also know an initial amount. We know that that initial mass is 100 milligrams. So we're going to measure in milligrams here, e to the KT power. All right, now we've got to figure out K in order to get this thing off the ground. But notice that's where the half-life comes into play. All right, the half-life allows me to say then that if I plug in 1,590 years, 1,000 e to the k 1,590, I'm going to get exactly half of what I started with. I'll have 50. All right, so now that I have that piece of information, I can figure out what k is. Okay, so let me make a note here. The half-life allows me to solve for k. And that's what this is about, okay? So now I know that e to the 1,590k equals 1/2. And taking the ln of both sides, I end up with 1,590k equals ln 1/2. All right, and then so k equals ln 1/2. Well, yeah, let's say ln 1/2 divided by 1,590. And we don't really like ln 1/2, so an easier way to say this is, remember 1/2 is 2 to the negative 1 power. And remember, with logarithms, I can take that out as, I can take out exponents as a coefficient. So this is actually the same thing as saying negative ln 2 over 1,590, which is kind of a neat way to rewrite that. Logarithms are kind of neat in that sense. So there's my value of k. Now, I could get that as a decimal, but actually, I don't really know why. It's probably going to be just as long to write the decimal as it is to write this expression. My function then, which is what I'm looking for here, mt, we're going to say is 100 e to the negative ln 2 over 1590 t power. All right. And notice that actually, remember, e to the negative ln 2 power is actually the same thing, or let's say e to the ln 2 power is actually the same thing as 2. So I could, if I wanted to, write this as e 100 times 2 to the negative t over 1,590. Yeah, and I got to be careful here. My parentheses, the t is being multiplied, not divided, right? So here I could, if I wanted to, say m of t is 100 times 2 to the negative t over 1,590 power. And that's why I didn't get a decimal, because I wanted to highlight that you could do that. But commonly, we kind of just stick with the exponential function. I mean, why not? Okay, now we have some, so there's our function. This is my function. But we have some other things we want to do. So in B part here, I want to find the mass after 1,000 years. And since 1,000 years is less than the half-life, I should get this value to be greater than 50, hopefully. All right, so here, all I'm doing now is plugging in 1,000 in for t. So that's going to be 100 e to the negative ln 2 over 1,590 times 1,000. All right, this is just something for the calculator to do. When you plug this in, you should get around 65 milligrams. Okay, and I advise please practice doing that in the calculator because it's very easy to miss that. Okay. All right, now in part C, what does it ask for? How long will it take to get this thing down to 30 milligrams? How long will it take to get this thing down to 30 milligrams? So this time we're trying to solve the equation mt equals 100 e to the negative ln 2 over 1590 t, that's the value we don't know, equals 30. So we're going to have to apply a logarithm here, right, to solve this equation. Okay, so not too bad though. We get, let me pick a different color. We get e to the negative ln 2 over 1590 t equals 30 over 100, which is 0.3. So now I want to take the ln on both sides. I end up with negative ln 2 over 1590 t equals ln 0.3, right? And then so I just basically multiply by negative 1590 over ln 2. And so I get t equals negative ln, well, let's do the 1590 first. Ln 0.3 over ln 2. And that as a calculation, and we get basically 2,762 years. So that's something we're going to let the intern take care of, right? We don't want to sit there that long. Okay, I hope this makes sense. Again, let me go over it real quick. The decay and the growth situations are basically the same in terms of the mathematics. The only difference is that for decay, growth is negative, and for growth, k is positive. And so what we want to do in both situations, we start off with our model. That's like this MT. We start that's our model. And then we use the given information, which is usually a second point. So in this case, we knew the half-life gave me my second point. And the first one, we knew the population in 1960. All right, we use that information to solve for k. You will have to use logarithms to do that, which is not a big deal. From there, we can just solve for whatever they wanted. So for b, for example, they gave me a value of time, asked me to find out the mass. So I just plugged in time in and solved. For part C, they gave me the mass and asked for time. So we're going to have to use a little bit of algebra, but we can still do it. Okay, I hope that makes sense. All right, now I'm going to give you another situation, another physical situation here. All right, let me go to the top. So these are my notes so far. Oh, I didn't start at the top this time. All right, Newton's law of cooling. Okay, when my son was real young and we'd bring out his soup or whatever, his pizza, we'd have to stop him from biting into it right at the beginning, right? Because, I mean, that's what you want to do. I burn my tongue on my coffee all the time. And I taught him at that time, I was like, look, you gotta wait because Newton's law of cooling, it's going to, as it's in a cooler environment, it's going to cool down. Okay? So just wait a second. And so Newton's law of cooling says that how quickly does something warm up or cool down? Well, it depends upon the environment it's in. So for example, if you're trying to warm up yesterday's pizza and you put it in the oven at 150 degrees, versus you put it in the oven at 400 degrees, in which environment is it going to heat up faster? The hotter environment. Okay, now this sets up as a differential equation just like growth and decay with a slight variation. So we say this time the change in temperature versus time, all right, so capital T is temperature, lower t is time, is proportional to the difference between your temperature function and the wherever you are, your ambient temperature. So this TS means atmosphere temperature. Right? So if you take it out of the oven into a 70-degree room, which is kind of a common thing we're talking about when our food cooling down, how long will it take to cool down to a comfortable temperature? This is the equation that models that. All right, now this is exactly the same as what we did earlier, even though we have this difference thing, because I can say this. Let's let y be this difference, T minus Ts. Ts is a constant, right? We're bringing it into a constant atmosphere. So if I take the derivative of that, so then dy dt is going to be, well, the derivative of the constant is 0, so I just end up with the derivative of t, dt ds. So this equation then could be written as dy dt equals ky. That's the exact same thing we did with growth and decay, right? Okay, so let me show you an example of Newton's law of cooling. And this is kind of a neat thing. All right, so let's look at example 3. And the book says a bottle of soda pop, and that just sends chills down my back saying that, right? We're in the South, we're in Jackson, Mississippi. We got to say a Coke. All right, so a Coke at room temperature is placed in a refrigerator. I'll just say a fridge, if that's okay. And here, the Coke, we should mention, is 72 degrees Fahrenheit, right? So it's at room temperature. We just bought it in the store, and now we're putting it into the refrigerator, and the refrigerator has an internal temperature of 44 degrees Fahrenheit. Okay. Now, after 30 minutes, all right, so that's going to help me set the model, but remember, I'm going to have to find that K value. I'm going to need another test point. So what do? We wait 30 minutes, and after 30 minutes, we get a temperature reading of 61 degrees Fahrenheit. So after 30 minutes, the Coke, and I'm kind of saying that with a little bit of with a little bit of a rebellious heart, right? We're in the South, we have to say Coke. We cannot say soda pop. So after 30 minutes, the Coke has a temperature of 61 degrees Fahrenheit, like that. Okay, now the question. So that's going to be our initial point, or our second point that helps me figure out K. The first question is, what is the temperature after half an hour? After another half an hour. So what is the temp after another half hour? So basically after 1 hour of us putting it into the refrigerator. Okay, good. So we are going to set up Newton's law of cooling, this equation, this dt equals k t minus ts. So the ambient temperature that this Coke is in, it's in the refrigerator, is 44 degrees. Okay, so we can say then that dt k t minus 44. All right, now we're going to do this clever substitution. We're going to let y be t minus 44. So then we end up with the equation dy dt equals ky. And we have an initial point here. So we know that when t is 0, we get what? How hot was the Coke at first? 72. So then y of 0 is, how do you get y of 0? You plug in 72 in for t. 72 minus 44, we get 28. All right, so that's what we have initially. That we have dy dt equals ky, y sub 0 equals 28. And just from what we've done already, we know then that my model, y of t, is going to be y of 0 e to the kt power. So we get 28 e to the kt. That's my function once we've done this transformation, okay? And then we can also figure out what the value of k is because we have a second point, right? After 30 minutes, we have a temperature of 61. So I know we have to convert that to a y value though. We know that t of 30 is 61 degrees. So that means then that if I plug in y of 30, I get, well, how do I convert that? 61 minus 44, okay, I get 17. All right, so then now taking my model here, when I type in y of 30, which is 28 e to the kt power, I know that's got to be 17. From there, I can solve for my value of t, right? So the way I do that, again, oh, and I forgot, I plugged in 30 for t, right? So I have e to the 30k power equals 17 over 28. So taking the ln of both sides, well, taking the ln of e to 30k power is what? 30k equals ln of 17 over 28. So finally, k equals 1/30th ln 17 over 28, which is approximately, if you plug that into a calculator, you get negative 0.01663. Right, that's my value of k. Okay, so now I know then my y value, my y function, is actually this 28 e to the negative 0.01663 t power. And I can convert that back to t because remember, y is simply t minus 44. So then my t, I just add 44 to this. So my t function, my t of t is 44 plus 28 e to the negative 0.01663 t power. And there is my temperature function over time. Okay, now the question asks for part A, it said, how cold is it after another half hour? So my A answer, I'm actually plugging in 60 minutes, right? How cold do we expect it to be after 60 minutes? 44 plus 28 e to the negative 0.01663 times 60. That's just a calculator question. You should get approximately 54.3 degrees. All right, is that cold enough? I don't know. I like my Coke to be 50 degrees when I drink it. I think you agree. So let's do for B part. Let's say, how long will it take to get to 50 degrees? Cool to 50 degrees. All right, so now we're just plugging it in. 44 plus 28 e to this power. We don't know t, right? That's what we're trying to solve. Equals 50. So it's just like the previous examples. You subtract the 44, you get 6. So you get e to this power equals 6 over 28. So then t is going to be the ln of that divided by this weird power here. So you get 628, ln 628 divided by negative 0.01663. And you get approximately 92.6 minutes. Okay, so about an hour and a half. You're going to have that Coke in the refrigerator for an hour and a half before it's going to be the 50 degrees that you want to drink. Does that make sense? Okay, now let me show you something kind of funny about Newton's law of cooling. So if you graph this t function here, if you graph that, there's going to be actually a horizontal asymptote at 44 degrees, okay? Because notice as t goes infinity, okay, this t of t approaches 44 plus, well, as t goes infinity, this e to this power is actually going to go to 0, right? Because that's a negative power. So you get e 1 over e to some power. It's getting larger and larger. That's all going to go to 0. So you end up, this thing's going from to 44 plus 0, which is 44 degrees. So the graph of this function looks something kind of like this. Starts out at 72, and then it's an exponential, a negative exponential with a horizontal asymptote, which means we'll never reach exactly 44 degrees. That's weird to think about. That means when you bake a cake and you pull it out of the oven and it's 315 degrees or whatever, and you just let it sit there, it will never hit exactly room temperature. Now it'll get so close to room temperature that we can't even tell a difference, but that's not exactly what we're trying to say, right? Okay, so that's kind of a weird thing. And I hope this all makes sense so far. Okay, now what I'd like to do is spend a little bit of time in 6.6. 6.6 is about inverse trig functions. So what I want to do is first kind of go over the trigonometry of inverse trig functions, and then we'll go back and clean up the calculus, and we'll probably do the calculus parts on Thursday. Okay. So let me come up at the top and start anew. So we're at 6.6, and we're looking at inverse trig functions. Now, inverse trig functions in terms of calculus are actually very valuable in themselves. Okay, but we kind of have to explain what they are. If you haven't seen it before, well, I'm going to clarify what we mean. Okay, so first of all, an inverse function, so a function looks like this. You have your set of x's, so this is my domain, and you have your set of y's, which we call our range. And we already talked about inverse functions earlier, right? You plug in an input, you get an output. That's what a function does. The inverse function will take you back from your y back to x, the x that you originally plugged in. And the only time an inverse function works is if your function is what we said is 1-to-1, which means it has to pass the horizontal line test. What you can't do is you can't have two y's over here trying to go back to the same x. No, I said that wrong. You can't have one y trying to go back to two x's, right? So here we can't, it must pass the horizontal line test. And we looked at that way back in early parts of chapter 6. All right, now the thing is though, when I look at the sine graph, sine kind of does this thing. All right, so this is y equals sine x. Sine x fails the horizontal line test very much, right? In fact, it's going to fail the horizontal line test an infinite number of times. Okay, for any horizontal line that we pick. So how on earth can we have an inverse trig function? So what we do, so let me make a note, to have y equals sine inverse of x, we limit the domain of sine x. Right, here's what we actually do. We take sine just from negative pi over 2 to pi over 2. And if you graph sine just over that interval, you start at -1, you hit 0, and then you go up to +1. All right, so that passes the horizontal line test. It also covers the full range of sine. And so when we're talking about sine inverse, we're not talking about a true inverse function. We're talking about an inverse of sine over a very limited domain, going from -π/2 to π/2. Okay, so what we can say here for sine inverse, we say sine inverse of x equals y if and only if sine of y equals x, and we're limiting our domain to between π/2, -π/2 and π/2. That's what we mean by sine inverse. Okay, we can do a similar thing with cosine and tangent. And so I won't really kind of go over the details of the graphs in that regard, but it's a similar idea. So cosine inverse equals x. Cosine inverse of x equals y if and only if cosine y equals x, and this time -π/2 to π/2 won't work, because remember cosine starts at 1. So at -π/2 to π/2, it won't pass the horizontal line test again. This time we limit it to 0 to pi. All right, so basically you can think for sine, we're talking about quadrants 4 up to quadrant 1. And for cosine, we're going from quadrant 1 up to quadrant 2, like that. And then tan inverse, by that we mean tan y equals x, and it's going to follow the same thing as sine. Okay, so we're in quadrant 4 and quadrant 1. Okay, and then we don't really deal with secant, cosecant, and cotangent inverse very much, but they would follow a very similar pattern. Another thing is if you see something like this, arctan. Arctan is the same thing as tan inverse. It's just another way of saying it. And the same with arc cosine and arc sine. Okay, those are all just other ways of saying sine inverse. Okay, I hope this makes sense. All right, now let me show you a little bit of some trig stuff involved with this. So for example 1, I want to find A, sine inverse of 1/2, and B, I want to know tan of arc sine of 1/3. Okay. All right, so another thing to think about here that I didn't really mention, but just to make it clear what we're doing, for a trig function, what is your input? Like when I say sine of something, my input I typically think of as an angle, right? You plug in an angle, like sine of pi, you get an answer out of that, a fraction. So sine pi is a bad example. Let's do pi/4. Sine of pi/4, you get the square root of 2/2. And those sides are related to a right triangle, right? Okay, so again, your input is what? Your input's an angle, your output is a fraction. Now, by the nature of inverse functions, what happens with sine inverse then? Your input is a fraction, your output is an angle. Okay, so when I see sine inverse, you got to remember that that is an angle. Okay, you're plugging in an angle. So it totally makes sense in B part to plug in arc sine of 1/3 because you're plugging in an angle, and out of that should come a fraction. All right, now for A, I'm looking for the angle. What value of theta such that sine of theta equals 1/2. And remember, we got to be in quadrants 4 or 1. Okay, so I think we can figure that out. When does sine theta equal 1/2? Yeah, pi over 6. So sine inverse of 1/2 is simply pi over 6. Okay. For B part, I got to figure out tangent of arc sine of 1/3. Let me think about that for a second. So here, what I know is let's let y equal this arc sine of 1/3. Then what does that tell me then? That sine of y equals 1/3. Okay, I can draw a triangle and understand what that means. So here's my angle y. Sine is what? Opposite over hypotenuse. So I have an opposite side of 1, a hypotenuse of 3, and from there I can use Pythagorean theorem. So I know that 3 squared equals 1 squared plus this other side. We'll call it, let's call it x squared. So then that becomes 9 minus 1, which is 6 x squared. So x becomes, that's 9 minus 1 is not 6, right? Is 8. So we get x becomes, we're just looking at the positive part here, square root of 8, which is another way of saying 2 root 2. So this third side is 2 root 2. So from that, notice what are we trying to find? We're trying to find tangent of, well, arc sine 1/3 is y. We're trying to find tangent y. So tangent of this same triangle is what? Opposite over adjacent. So that's going to be 1 over 2 root 2. Or if you rationalize that, you get multiply root 2 over root 2, you get root 2 over 4. Okay, and depending on what book you have, this is acceptable. Some books would prefer that. They're the same value though. Does that make sense? So for these, when you have a trig function with an inverse function plugged in, do this clever substitution. Let y be that expression, and then from there you can draw your triangle and figure out what you need. Okay? All right, let me try another one here with some cosine stuff. So I'm kind of bouncing around from the book's examples a little bit. This is example 3. We want to simplify actually, we're not ready for that one yet. Okay, so what do I want to do? Actually, why don't we save the rest of this for Thursday? I think we've done a good job of introducing what inverse trig functions are. Now what I want to do on Thursday is look at the derivatives of those and maybe some integrals related to inverse trig functions to show you that this sounds like it's going to be really complicated. It's actually not too bad, and it's actually extremely useful. Okay, so I hope this makes sense. I'm going to have these notes posted for you. If you have questions, let me know. I'd be glad to help. Hope you guys are doing well, and we'll talk to you later. Have a good day. Take care.